Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tier. Hope you guys all had a good Thanksgiving. I wasn't able to make any videos yesterday because I was with my friend and his family celebrating Thanksgiving. But anyway, I'm back today. And today I'm going to go over another recent daily math problem I posted. Nobody solved this one. I was a little bit surprised. But anyway, the problem I posted involved what are known as reduced imaginary quadratic forms, or if you like, reduced quadratic polynomials with negative discriminant, which are pretty much the same thing. Anyway, let's begin. So here's the problem statement. We say that a quadratic polynomial, which is just a polynomial of the form f of x equals ax squared plus bx plus c, we say that such a polynomial is reduced if it's so it has a negative discriminant, first of all. Those are the ones that we're considering. And negative discriminant, the reason these are called imaginary sometimes is because the roots are imaginary. I mean, remember, quadratic formula says that the roots are minus b plus or minus square root of b squared minus 4ac over 2a. Well, that quantity d, b squared minus 4ac, is a quantity in the radical, in the numerator. And of course, the square root of a negative number is an imaginary number. So it follows that the roots of a quadratic polynomial are imaginary precisely when the discriminant is negative. Anyway, for such a quadratic polynomial, we say it's reduced if the coefficients a, b, c, first of all, they all have to be integers, and then they have to be pairwise relatively prime. So in other words, the GCD of a, b, and c is 1. But we also require that the absolute value of b is less than or equal to a, which in turn is less than or equal to c. In other words, A and C are both positive. B doesn't have to be positive, but its absolute value has to be less than or equal to A. And also, if whenever A is equal to the absolute value of B, we require that B is positive. Or if A is equal to C, we also require that B is positive. There's a technical reason for defining these things, which I don't think I really want to get into on this video, but it has to do with algebraic number theory. It turns out that you can transform any quadratic polynomial. It doesn't have to be reduced, but you can apply a linear transformation. Usually, you use what are called forms, which are sort of the equivalent homogeneous polynomials in two variables. F of x y is ax squared plus bxy plus cy squared. And then it turns out that there's a unique linear transformation. Just a matrix you can multiply the vector x, y by to make it reduced. That's why we like reduced quadratic polynomials. Also, there's a finite number of them. For any discriminant, it turns out that there's always a finite number of reduced quadratic polynomials with any discriminant, whether it's positive or negative. There's sort of a different rule for defining reduced quadratic polynomials with positive discriminant. It always turns out there's a finite number, and that number is known as a class number. So we write C of D. C of D is just a positive integer. It's just equal to the number of reduced quadratic polynomials with discriminant D, whether they're positive or negative. And like I said, it's always a finite number. And it's a very useful thing to know, too, in terms of algebraic number theory. I'm not going to bother explaining it, but these are very important. Anyway, so what the problem is asking for here is, first of all, for part A, I'm asking you to find all the value or possibly multiple values of the discriminant D with D between minus 100 and 0, such that the class number D, C of D, is maximum. And then for part B, I put a star here. I don't know why I put a star here, because actually I think part A is the hard part. But then I say for each such D, find all the reduced quadratic polynomials with this discriminant. I think I should point something out before I continue, actually. I have a PhD in algebraic number theory from UC Berkeley. It's what I did my thesis in. And there are advanced methods. I'm not going to go over them here, but there are some very clever advanced algorithms for computing class numbers without having to compute all the reduced quadratic forms or to reduce quadratic polynomials. And maybe that's why, in general, it's a lot harder to find them all than to compute the class number. But for what we're doing, the way I solve this problem is just use brute force. This is an easy enough problem to solve using a computer search using brute force, which is how I did it. And we could even do this by hand. I mean, it's not that hard. I mean, I guess going through all the discriminants up to a minus 100 is hard by hand, but actually, I'll just tell you what I did. I wrote code to find, or I used the built-in mathematical code to find the class numbers of all the quadratic number fields with discriminant, between minus 100 and 0, and the solution turned out to be minus 95. And then I could just do this by hand. I didn't even need a computer to find all the reduced quadratic polynomials with discriminant minus 95. But anyway, that's a little bit of a sidetrack. Let's just go over the solution here. So this is a mathematical code I wrote to compute all the reduced quadratic polynomials. I call them reduced imaginary quadratic forms here because that's kind of what you use if you're in the algebraic number theory field, but it's the same thing, like I said. And maybe I should just go over this code. This is actually finding all of them. So finding all the polynomials. In other words, all the coefficients A, B, C of every quadratic polynomial ax squared plus bx plus c, whose discriminant has some fixed value d. And I'm assuming d is negative here. So here's how you do it. I mean, you really just kind of. So I have two for loops here. First, I'm looping over a. So I'm letting a range from the minimum value of a is 1, obviously, and a has to be positive. And we also have, it turns out that 3a squared has to be less than or equal to minus d. You could check that yourself. I mean, d is b squared minus 4ac. Remember, d is negative. So if you like, minus d is 4ac minus b squared. But remember, we also have to have a is less than or equal to c. And if 4ac minus b squared is less than minus d, it follows that 4a squared minus b squared is less than minus d. But we're also requiring that b has absolute value less than or equal to a, which also implies that 3a squared is less than or equal to minus d. So you can check that yourself. That's kind of a mouthful, but it's true. And then similarly for c, so c has to be at least a. Remember, we're requiring that a is less than or equal to c. So we start c equal to a, and then now we're requiring that c3ac is less than or equal to minus d for the same reason I said earlier. And now, once we have a and c, b is fixed because we're already fixing the discriminant d. So you can solve for b. B is just a square root of d plus 4ac. We could just do that using algebra, using the equation for d, which is b squared minus 4ac. So the next thing we have to do, b doesn't have to be an integer if we do this. And in general, it won't be. But for some values of a and c, b will be an integer. So if it is an integer, we also have to check that b is less than or equal to a, because of b could also be greater than a if we did this. And then if it is, then we add abc to our result. So it means ax squared plus bx plus c is indeed a reduced quadratic polynomial of with discriminant d. But it's not the only one necessarily. We could also have a minus bc. Remember, I'm defining b here to be the positive square root of d squared plus 4ac. Well, there's also a negative square root. And you have to be a little bit careful here because remember we have the requirement that B has to be strictly less than A in order for A minus BC to also be reduced. And then we also, I didn't want to duplicate my results, so I'm required that B is non-zero. So if we do that, we get a second form, A minus BC, or AX squared minus BX plus C, whose discriminant is also D. So this will find all the reduced quadratic polynomials of discriminant D. Anyway, so that's the first step. That's the first thing you have to do. But then once you've done that, well, then you just kind of run this. You know, what you end up doing is um, you, oh, you also have to look for the one with a maximum class number. So, oh wait, I'm jumping the gun here. It looks like, uh, yeah. So what? Then there's just a one line. There's a one line function you can write called class number of D. It just counts the number reduced to imaginary quadratic forms of discriminant D. So we really did the hard part already. The previous function I showed you is a pretty long function. Um, you know, it's this function here. I don't know, it's about 20 lines long. It finds all the reduced quadratic polynomials of given discriminant. But once you have that code, you can just count them. So you can, you know, this is a very fast code to run on my computer. Uh, yeah, and so you can just use it to find all the reduced quadratic forms within some range. In this case, between discriminant between 1 and 99 inclusive. So and then you just keep track of the well, I'm jumping the gun again. I mean, for a given discriminant D, you just find the length of you know, because I put these things in a list. You know, I put all the triples A, B, C into a list, and then the length of that list is just the class number. So that's why we just need one line of code to compute the class number of D. Um, and the table on the bottom shows the results. And I think I should clear something up here. Actually, you'll notice that the left column of all these, I broke up the table into 10 pieces so it's easier to write it down. But for each of these pieces, there's 3 columns, and the first column is a class number. The second column is second column, no, the first column is a discriminant. Second column is the class number that I computed using this function called class number. That's what we want. But the third column, it turns out there's a built-in Mathematica function, which I think I've already explained. It's called number field class number. And this will compute the class number of the, in this case, the quadratic number field generated by the square root of minus d. Unfortunately, that's not equal to the number of reduced forms of discriminant d because, uh, well, it's just not. I mean, you know, it turns out the discriminant of a quadratic polynomial has to always be congruent to 0, 1 modulo 4. That's easy to prove because d is b squared minus 4ac. I think you can check for yourself that that always had, you know, b squared is always 0, 1 mod 4, and 4ac is obviously always 0 mod 4. So um, it follows the discriminant is always 0, 1 mod 4. That's actually true for arbitrary number fields, not just quadratic ones. But anyway, so I just for comparison, I'm showing the number field class number, the built-in mathematic function, but we should only be looking at the ones where d is either 0, 1 modulo 4. In other words, minus d is either uh, 2 or 3 or 4 mod or 0, 3 modulo 4. And then for the other cases, the way I'm computing it's equal to 0. I think you'll notice there's a lot of entries in this table that are 0 in the second column, like -1, -2. Specifically, all the ones where the discriminant is 2 or 3 modulo 4, because those aren't defined, and you always get a class number of 0 the way I'm computing it. So we really only care about the numbers in the second column here, no, not the third. And And you can sort of do this by inspection, which is what I did originally. And if you look by inspection to see what's the largest value of CD, in other words, the largest value in the second column, turns out to be 8, and that's unique. And that turns out to occur when D is minus 95. It's almost at the end of this table. I think you see the country in the last region here. D is minus 95. The class number I computed with this function class number is 8, and the other one agrees with it. The one the built-in mathematical. So the largest class number is 8, and uh, the corresponding discriminant is minus 95. And I mean, what if we were asked to do this where we were looking up to discriminant equals minus 1,000 or minus 1,000,000? You wouldn't want to do this by inspection. So I actually wrote another function that will automatically do this, and it's pretty straightforward to do this. I have a function here called maximum class number, and maybe I should just explain what it's doing here. So it's really just looping over all the discriminants in the range we're interested in. In this case, for our case, it's going to be D min is minus 99 and D max is minus 1. So you have a for loop. You actually have two for loops of D going from D min to D max. In the first for loop, you first compute the class numbers of all the discriminants, and then you set the maximum. You just kind of go through all the class numbers and keep updating the maximum. But then you have to go through it again. You have to look for the maximum. And once you found the maximum, you append the value of D and the corresponding value of C. So in this case, there's only one class number, one discriminant with maximum class number 8. This thing did check itself and find that 8 was the maximum class number, and that occurs for the unique discriminant of minus 95. So that's pretty much, and then there's one last thing we have to do once we've done that. That's kind of the solution to part A, but like I said, part B was really the easy part of this, because that was the first thing I did here. When I did this brute force, I wrote this function reduced imaginary quadratic form. Well, now we just run it. So now we just output, we look at its output, and here it is. These are the coefficients A, B, and C of all the reduced imaginary quadratic forms with discriminant 9 minus 95. I even did this in my head before I ran this thing. I didn't really need to run this thing because they're not that hard to find, but here they are. You got the first one is x squared plus x plus 24, and then you got 2x squared plus x plus 12, and in this case, since B is less than A, we can take its negative. We got another one, 2x squared minus x plus 12. And then you get a couple more pairs like that. You get 3x squared plus x plus 8, and 3x squared minus x plus 8, and 4x squared plus x plus 6, and 4x squared minus x plus 6. I think the reason you get a lot of these is because 24 has a lot of divisors. So 6, 8, 12, and 24 are all divisors of 24, and they all give rise to some of these reduced quadratic forms. But there's one more. Notice that all the first 7 of these all have B equal to plus or minus 1. Those are sort of the easy ones to find. But it turns out there's one more where B is 5. So you have 5x squared plus 5x plus 6. That one's harder to find by hand. That's sort of the odd man out here. So those are the 8 reduced quadratic forms, or if you like, quadratic polynomials of discriminant minus 95. And that completes my solution to this problem. So that completes this video. Thank you for watching. Long live math. I'll see you guys next time. Bye.